Hello, welcome to our lecture course on quantum gravity. So we are at chapter 1. So last time in 1.1 I gave you the main motivations why we have to deal with quantum gravity. I also introduced you into the necessary scale, the Planck scale, and discussed why this is so remote from our everyday scale. Today I will finish that chapter 1, and part of it will be the discussion of what is called the fundamental semiclassical theory. So what is that? Now, what we mean here in that context is the so-called semiclassical Einstein equations, r mu nu minus 1/2 g mu nu r plus lambda g mu nu. And then if you recall, classically, at the right-hand side, we had here 8 pi g over c to the 4th and the energy momentum tensor. Now, if matter and actually all forms of energy are quantized, then, this cannot stand as it is. If you think about the standard model of particle physics, the leptons, the quarks, everything would be here, and this would in fact be an operator. So, but if you have an operator on the right hand side, then of course you would have here operators also here, and this would already lead to full quantum gravity. But what is meant here is that, okay, we have here an operator which are symbolically denoted by this hat, and then we take an expectation value here of, say, some quantum field. So in the Schrödinger picture, this is stands for functional Schrödinger representation. So the psi is a function of all fields. Of course, in the limit of quantum mechanics, it's just a quantum mechanical wave function. Now, this is an ad hoc equation, certainly, and it would mean that if it were exactly valid, that we would perhaps not need to quantize gravity, because this is perfectly classical, and this is also classical. This is what I mean fundamentally semi-classical. Of course, you might have, or anyway expect such an equation at in a certain approximation. And later in chapter 5 or so, we will discuss that when we have canonical quantum gravity and we derive the limit of quantum field theory in curved space-time, then we can get such an equation as an approximate equation. But that's not the issue here. The issue here is, can we have this at an exact level? The semi-classical can mean many things in physics, and here it just means that equation. And it was discussed, maybe not the first person who did it, but certainly one who discussed that at some length, by Möller in 1962, and of course by many others. This question, whether this can be exactly valid, is part of a more general question, whether we can have a so-called hybrid dynamics, a hybrid dynamics between a classical gravitational field and quantum matter, independent of the exact equation. So that's a question. Now, over the years, and the history is certainly very interesting and illuminating, people have put various arguments in favor of either, this can be or this cannot be. Bryce DeWitt, for example, in 1962, he discussed models where he had two different systems that interact with each other, and one a quantum system and one an other system, and he concluded that due to the action, if you have for the quantum system, say, the uncertainty relation, then necessarily you have them also for the other system. So if you have a quantum system, this is what DeWitt says, that whatever you couple to it must also be quantum. To quote him, he wrote, "It is shown in a quite general manner that the quantization of a given system implies also the quantization of any other system to which it can be coupled." Now later in the 70s, there was an influential paper by Epley and Tanner who discussed the coupling of a classical gravitational wave to a quantum system, and concluded there are inconsistencies if gravity is not quantized. I will say some words later about that. So maybe I should just write the names down. You can read about them in my book and elsewhere. all the details, and you have also the references there. Epley and Hannah. Now, my statement here that this is not quite correct. I mean, what you can certainly have is when you have a system A coupled to a system B, that uncertainties in one system are transferred also to uncertainties in the other system because of the coupling. But this can also be classical uncertainties. So what David analysis shows basically is that if you have some, even if it's classical noise, in one system it's transferred to the other by an interaction. But you cannot conclude that if system 1 is quantum, the system 2 is also quantum. Yeah, you may wish, for example, to discuss, to read about this in our paper that we wrote some years ago together with two others, so in PhysRefD 78 2008 064051. No? So there it is shown by a detailed analysis of David and Epley and Tanya that uncertainties from one system are transferred to the other, but not necessarily quantum, and that in fact one can write down a hybrid dynamics for an exactly classical gravitational field coupled to a quantum, say, system of electrons and so on. Whether this is a natural theory or not is of course another question, but at least you can write it down. I mean, the example given here is not the example given here. So one must be careful by making such statements about, say, the necessity of quantizing a gravitational field. Now, in this context, and I return to a detailed discussion of this later today, but in this context, one often reads in the literature about an old work by Bohr and Rosenfeld about the necessity or non-necessity of quantizing. At that time it was electrodynamics, but you can also take the arguments for gravity. No? So historically important. There's the paper by Bohr and Rosenfeld from the year 1933, so a very old paper, and the motivation was the following. I mean, this was the day, the times of the advent of quantum electrodynamics. So quantum electrodynamics, the first papers were written at the end of the 1920s, and there were problems coming up with that, and people were not really sure how to understand quantum electrodynamics. And there was a paper in 1931 by Landau and Peierls, and they claimed that for electromagnetism there's an uncertainty already for a single variable, not just for conjugate variables as in quantum mechanics, P's and Q, but for the Q itself. And they claim this is then in 1931 that quantum electrodynamics actually has no fundamental meaning because the commutation rules that we have there in the formalism cannot be checked, because already for a single quantity there is a problem. And Bohr and Rosenfeld, by a very detailed and one must say complicated analysis, showed that this is not true, that actually measuring electric and magnetic field is in accordance with the canonical commutation relations, and that there is no limit, no uncertainty for necessarily for a single quantity. So they were concerned about the measurement, so measurement analysis of the quantized electromagnetic field. Just to give you an idea about that, what they did, so they considered a test body. I mean, this is symbolized here. This has a mass m and an electric charge q. Yeah? And so there is an electric field, maybe for simplicity here, in one direction, which is supposed to be the x direction. So there's an electric field E vector, which is E times Ex. So that's the x direction here. And let us assume that all this equipment is in a box with a certain volume, and so there's a certain length scale here, L, and we have a volume of the order L cube. I mean, this is a heuristic analysis, so we are not concerned with numerical factors. Now, the task is that this is a macroscopically charged particle or body. It's a body. Should that you use this to measure the electric field and see if there are some limits. So measure the. In fact, it's the averaged, not a local. You cannot measure it at one point, so that you have to smear it out over a certain region. Measure the averaged electric field E of macroscopically charged body with electric charge Q. And one does this by measuring, of course, the force. So you have this classical relation F is Q times E, and this is, of course, a change of momentum in a certain average time. So you make a momentum measurement at the beginning and end of a time interval. Now that's what they assume. They make some assumptions. You can always criticize assumptions, but in order for this to work, for example, the back reaction onto the body should be small, and so because if the body is widely moving around, then you cannot use it. So the momentum should not be disturbed. So they make basically two assumptions. So the first is that that the electric charge is not too small, not too microscopic, and so it should be bigger than h per c. Recall last time we called this the Planck charge squared, and this is around 137, the electric charge of the electron. And also the second assumption is that L should be bigger. I mean, this volume and this length should be bigger than Q squared over mc squared. You can interpret this as follow. It would mean the Q squared over L is smaller than mc squared, so the electrostatic energy Q squared over L is smaller than the rest mass. And then Bohr and Rosenfeld make a very long and complicated analysis. And I have not met many people in my life who have really read and understood the details of this long paper. But anyway, this long and complicated analysis led to the following, that you have uncertainties of that electric field that obey the following relations. H bar C over Q, and delta E times L cube is bigger than H bar over C, Q over M. So that's the variance in the sense of quantum theory. And they derive this as necessary conditions from that. So you cannot make this measurement analysis without obeying these equations. And okay, as I said, historically they were doing that as a reaction to Landau and Peier's paper to see whether there are limits for a single quantity. And this you see here is immediately clarified here, because here you have the charge and here you have the charge over m, and you can make them, I mean, in principle, arbitrarily small, these right-hand sides. So you cannot have delta E is bigger than, say, something that only depends on H bar and C. No? So this here can be made arbitrarily small, and so which means that E can be measured with arbitrary, in principle, precision. So the limits that Landau and Piles had claimed 2 years earlier, they were, of course, doing correct calculations, but the point is, this was not a universal result. You can find a situation where you can really measure it precisely, even if in that Landau-Pyle situation it is not possible. They, moreover, I mean, Bohr and Rosenfeld, moreover, showed that the results here, they lead to, well, that their analysis leads to results that are consistent with the canonical commutation relations of quantum electrodynamics, which are between electric and magnetic fields. No? So results of this measurement analysis are consistent with the quantum commutation relations. Of QED, of quantum electrodynamics. So they have not shown what you sometimes read in the literature, that one has to quantize electrodynamics. This is not shown in Bohr and Rosenfeld. What they show is that quantum electrodynamics, the formalism, is consistent with a measurement analysis. As in quantum mechanics, you know, there are these Heisenberg microscopes and all the other things where you check the uncertainty relation. Of course, in this measurement analysis, I mean, the results are consistent with the formalism, as they should. And they showed in a much more complicated situation that this also holds for quantum electrodynamics, for field theory. They did not show that one is forced to quantize electrodynamics. But we are here actually not interested in discussing details of QED, that no one doubts that this is a quantum theory, but we are interested in gravity. Now, people later tried to extend Bohr and Rosenfeld to the gravitational field. And there's a book in the 1980s von Bodziskowski and Trader, and there are also other papers. Let us check whether we can heuristically do that. No? So heuristic discussion for gravity. Yeah, so here, well, of course, for this it's sufficient to go to the Newtonian limit. So in the Newtonian approximation, we have G00, as you know from relativity 1, is given by -1 plus 2gm over RC squared. So the Christoffel symbols from there, of course, they have many components, but for the heuristic analysis, they typically, the gammas, they are, derivatives of this. So here you have to differentiate this with respect to R, basically. So you have here that the gammas are then of the order Gm over R squared, C squared. So I should make quotes, but I think it's clear what it means. No? So here, of course, in electrodynamics, we have E is Q over R squared. In the electrostatic field, it would mean that we can somehow identify this gamma with the electric field, but of course we have to take care for the factors. So from here, we translate epsilon into gamma times c squared over g, no? So that we have something like m over r squared, and the q we transform into the mass, but I write here mg, it's the passive gravitational mass. Passive gravitational mass. To distinguish from inertial mass here. And then, say, let us assume, for example, this relation. Yeah, and just let us transform then this and this here on both sides. Then we get that, okay, delta gamma. Okay, we have then this factor c squared over g times L cube. Must be bigger than h bar over c. And then we have here q is the gravitational mass, and this is of course the inertial mass here, like in electrodynamics, so mi. From what we get, that delta gamma times L cube is bigger or equal than h bar g over c cube, mg over mi. Now you see here that, if you recall from last time, is the Planck length squared. And here, this now is of a different caliber than this here, because here this you can make arbitrarily small in principle, but here this you cannot change. I mean, due to the equivalence principle, they are in fact equal, and so this is just a factor 1. No, gravitational mass over inertial mass. So what you get here is then something like that delta gamma is of the order Lp squared over L cube, or if you go to the metric, which is the integral of that, then you have delta G is of the order of Lp over L squared. So that would be then the result of this heuristic analysis. So you see there are some differences. No? So whereas for electrodynamics, Landau and Pius were certainly wrong, there are no limits here. At least if you naively extend Bohr-Rosenfeld to gravity, you find a limit here to that. So it seems that, say, the measurement of a single quantity like a metric component can be operationally restricted. And that is, in fact, in principle, possible in quantum gravity. As we will discuss later in loop quantum gravity, it also is in string theory, there are claims that there is a fundamental length scale, for example, and you cannot go below that. So then would you say, so limit to the measurement of a single quantity. Okay, this does not mean that quantum gravity is useless. It means that in these restrictions you see maybe some discrete structure or so of space-time, but that in other situations, and we have to discuss that later, quantum effects of the gravitational field can be really measured. Yeah, so I will even later at least quote one example. Now you find, especially in the older literature, much discussion on this. I can recommend, the thick book by Miesner, and Wheeler, and if you go to the later chapters, so there is a nice summary of this, and also some other heuristic discussions of these limits. So for me, here the summary is that there is a difference between gravity and electrodynamics, and it shows here in a potential limitation on the measurement of single quantity due to the existence of, say, a fundamental length scale. But this is heuristic, and we have to first construct a theory of quantum gravity and see how this is realized or not. I should mention also other important people, and I have no time to discuss them here in the lectures, but you can read in my book and elsewhere, for example, Bronstein, one of the pioneers in quantum gravity, whom you will hear about also then in the next chapter when we discuss the linearized gravitational field. He made in the 1930s, say 1936, or the years a bit earlier. I mean, had this tragic life, being killed in the Stalinistic terror in the Soviet Union of the 1930s. But he made, among many things, this Gedanken experiments, where he also derived such relations independent of this Bohr-Rosenfeld analysis. For example, he carefully noticed that the dimension of a body cannot be smaller than its Schwarzschild radius. So before discussing really black holes, and so he already noticed there is a limit of having the size of a body, because otherwise you will have gravitational collapse. And from that he gets also such relations with different powers here. And he from this claims actually that there's a limit to Riemannian geometry. Riemann geometry that is based on a continuous picture of space and time. And for him, Bronstein and others, already at that early time, this type of analysis points to a limit of the continuum picture. Maybe I cite him in English translation. After having made this analysis, he wrote, the elimination of the logical inconsistencies connected with this, I mean, when he discussed the Schwarzschild radius and so on and the limits, requires a radical reconstruction of the theory, and in particular the rejection of a Riemannian geometry dealing, as we see here, with values unobservable in principle, and perhaps also the rejection of our ordinary concepts of space and time, modifying them by some much deeper and non-evident concepts. Of course, these much deeper and non-evident concepts then refer to the task of quantizing gravity. Okay, so far for this excursion to Bohr-Rosenfeld and related issues. Let us now return back to the semi-classical Einstein equation here, as one particular model of an approach where you could perhaps have the idea that quantum gravity is avoided, because if this is the fundamental equation, then you're finished and you don't have to go further. Now, if you have this equation, I mean, here let me skip the cosmological constant, and we have here the Einstein tensor, so g mu nu is 8 pi g over c to the 4th, and then we have psi d mu psi. So this is meant as an operator. I do not always be as pedantic and write heads, or I could, maybe for the time being I should. Now, there's first a formal problem. If you want to calculate this, of course you have to go to quantum field theory. Then you see this is infinite, naively. Like in quantum field theory, you know, because of infinitely many degrees of freedom and because of space-time continuum assumed here, such things you have to sum over infinite terms and you get divergences. So you have to first think about regularization and renormalization in the sense of quantum field theory. And okay, we will partly discuss this in the next chapter. Partly it will require additional terms like curvature squares and so on in the action, which, if you start from a different action, will also modify this. So it's not so clear what is to be done in general. But at least if one sticks to that equation, one can prove that, I mean, the renormalized value of this, if it's done, is unique up to some well-defined term. So Robert Wald, in 1977, he showed that T mu nu renormalized, this is what REN means, is unique up to some well-defined terms. I mean, containing the metric, the Einstein tensor, and two other covariantly conserved tensor. Of course, you have to make some general assumptions about that, but yeah, at least so if you do that in a quantum field theoretic way, then you can make sense out of this equation, this formally. So that will not be the issue here in 1.2. I mean, we will discuss here the issue about whether there are conceptual problems with having this, even if it's mathematically well defined. So people have discussed over the years problems. For example, there may be a stability problem with this equation. So, for example, if you have a perturbation of small perturbation of Minkowski space, that you have exponentially increasing solutions of this, and you cannot stay close to Minkowski space. There is some uncertainty about this in the literature, but at least it's a potential problem. Also, in extremal situations, for example, this may not exist. So this here may not exist in extremal situations, such as situations with so-called chronology horizon, where you which separates regions with normal from regions with unnormal causal behavior. I mean, there are, of course, in global space-time with causality issues many delicacies, as you know from Kerr black holes and others. And if you go to such situations which are far remote from laboratory, then there may be some problems here. Also, I mean, this semi-classical equation brings in an additional type of nonlinearity that some people find confusing. For example, Paul Dirac, who also commented on this. He find that this is the reason, or was the reason for him to reject the semi-classical theory, this new strange theory, this new type of nonlinearity. So, new type of nonlinearities. The point is, of course, this here also obeys an equation, and we can go to the functional Schrödinger picture. And in the functional Schrödinger picture, of course, this obeys the functional Schrödinger equation, and this depends also on the metric itself. So you have I h bar, if I write it in this quantum mechanical way, psi dot. Of course, you can write it in a field theoretic way, is then the Hamiltonian, which is part of that here. Just of psi g, and of course this depends on the metric, so definitely this also depends already on the metric, which in principle is to be determined by this equation. So this contains the metric, but you get the metric by solving also this equation. So you see there's a really a non-trivial action and reaction on this. So if you have, say, a metric G1 that comes from a solution psi1 of this, and you have a metric G2 that comes from another solution, then, of course, this is linear, so has a superposition product psi1 plus psi2, but this does, of course, not correspond to, say, a sum of this, or even a very simple relation between this, no? Because you have to solve this full nonlinear actually integral differential equation, so which already prevents you from making too much use of this in practical calculations, and it's not so clear how you can relate, I mean, psi1 so yeah, to what this, I mean, it's very complicated. So there's no simple relation between the metric that belongs to this and G1 and G2. There's also another problem that was in fact even discussed in a real experiment, and I cannot avoid doing that here. So we have a Gedankenexperiment first, and a real experiment that was done by Page and Gaker in 1981, and it's the following. It looks a little bit like a Schrödinger cat type experiment, but it's of a different style. So you have a box, and you have a radioactive atom. Okay, but the Schrödinger cat, then of course, then if there's a radioactive decay, then there will be some poison and the cat will die, and so you have superposition of dead and a live cat. Here it's a bit different, so you have here a counter. So if the atom decays, then the counter is triggered and the following happens. So we have here two masses, and because we are interested in gravity, so we have two masses here, same or equal or different, that at the beginning they are here have this spring, or they're connected by the spring all the time, but at the beginning there are here some rigid connection. So rigid connection at the beginning, and outside we have a Cavendish balance that reacts on the gravitational field here, a Cavendish balance, and an observer, of course, here. This is U, and this, okay, is a radioactive source. So if the radium, if the atom decays, then the counter is triggered, and this rigid connection is destroyed, which means that the masses are only connected by the spring, and they can then approach each other, and also by the string repulsion recede. And before that they are just static, and after that they can oscillate, and then of course you can measure the configuration of the masses by the Cavendish balance, because the gravitational field you can measure outside without looking inside. I hope that this is clear, and let us make a simple model for that. I follow here an article by Unruh in the Festschrift of the Witzig's birthday. So simple model, Unruh 1984. So it's a bit simplified compared to the earlier analysis. So let us call the state 0 the quantum state of the masses at rigid connection. So quantum state of masses with rigid connection, and let us call 1 the quantum state of the masses with a spring, the spring connection of the two springs here. Okay, so the Newtonian approximation is certainly sufficient for that. We don't have strong gravitational fields, and instead of the full T mu nu here, it is sufficient to have here the Hamiltonian, which is a T00. Now that's fully sufficient for us. So the assumption is at some initial time, which we take to be 0, we have this initial state. So just this rigid connection, and then at later times, of course, we have the decay of the atom, and depending on that decay, you have the transition into 1. So we have here then a superposition. Psi is then with time-dependent coefficients 0, and 1. And okay, so we can at least approximately use the exponential decay law of radioactivity. So we can assume that, I mean, the square of this is, say, it's not exact, certainly valid, but it's some e to the minus lambda t. Yeah, and this here is approximately 1 minus this. So depending on the decay, and this is, I mean, depends on this decay constant, we have here this going into the superposition. Okay, now we are interested in having this term here, discussing this term here, and but only for the Hamiltonian. So we are interested in psi h psi, which depends on t, and this is assumed to be, according to this equation, the source of the gravitational field, right? So this is what if this equation is correct, what you would expect here to be measured. This gives you the metric, and this is measured here. And okay, you can calculate this here. So this is alpha t squared. You have 0 h0 plus beta t squared 1 h1, and then you have the interference term 2 real part alpha star beta 0 h1. Now comes a difference to the Schrödinger cat experiment. In the Schrödinger cat experiment, the issues about the superposition of dead and alive cat and about this interference term. Here we can assume that this interference term is approximately 0. That, or in other words, that these states are approximate eigenstates of H. So there is then no overlap. We are not interested here in discussing interferences. We can assume that there is so-called decoherence between macroscopically different states. I mean that 0 and 1, they are macroscopically different, and their interference is negligible. So we can have here decoherence. So no Schrödinger cat experiment. So the point is, because we have the expectation value, we have these two terms. Yeah. So we have here then that psi h psi of t is then approximately, I mean, e to the minus lambda t 0 h0 plus 1 minus e to the minus lambda t 1 1. So this is corresponds then to the situation where the masses are this is rigid, so they don't approach each other, and here this is where they can approach by the spring. So if this were then the correct equation here, or the correct result, that would mean that this would give you the gravitational field that you could measure. But you see here, you would expect then this Cavendish balance to react according to this time behavior, and so I mean continuously move around back and forth. But this is not what you would naively expect, and also not what was shown in the experiment, because what happens is that, okay, you have the initial things, and at some point it will just move. So as if you had, so to speak, a collapse of the wave function and that. No? So this here, is in contradiction to the experiment, where you have a sudden reaction of the gravitational field of the Cavendish balance. So this is also what you would expect, say, in a linear theory of the gravitational field, where you don't have expectation values, but where you have various components in a superposition of the gravitational field, and you are then in a component, of course, like in the Schrödinger cat, where you can see the masses then approaching each other or not, right? So which would at the end correspond to so-called Everett picture, of course, of quantum gravity. But you would certainly not expect in this here, no? Where you would have this kind of sum of two expectation values. So this is of course a very simple situation, but it's very nicely investigated and even confirmed in a real experiment. So you see that a naive ansatz of this can lead to problems immediately, even experimental problems. So whatever you have here, maybe as an equation, maybe you expect this to hold. You have to, of course, to discuss here the problems connected with this. And this is certainly a strong argument that you have against having this as an exact equation. Now, what is special about this situation here is that the fluctuations, the quantum fluctuations or the mean square deviation of this here is big, like also in Schrödinger's cat. It's not something that is concentrated like a narrow wave packet about one or the other. The point is, I mean, the separate masses and the approaching masses is really a very different situation. And here you have a large quantum fluctuations. And actually that's the situations where you have problems with that. Here H has large quantum fluctuations. And this is also the case in other situations. For example, also in other situations. For example, something very important that Ford discussed already in 1982 and which I described also in the book. These are the situation in linearized quantum gravity. Now, linearized quantum gravity we shall do the next time. We have not yet done, so I will not do a lot of formalism here. But depending on the quantum state in linearized quantum gravity, this equation gives you very drastic differences from, say, full quantum gravity. So this is radiation here of gravitational waves in linearized quantum gravity, what we will have next time. And so what he did, he first discusses the situation in the semiclassical theory, has some result about the emission of gravitational waves, and then he discusses the same situation using linearized quantum gravity to be discussed here. And he finds differences depending on the quantum state, because here you always have these expectation values, but if you go to linearized quantum gravity, then you can also have 2-point functions. I mean, so psi, I mean t at one point and t at another point psi, which you don't have here. And you can even have a quantum state where you have no radiation at all in the semiclassical theory, but you have emission in linearized quantum gravity. So in principle, if you could measure, it's not possible because it's too small effect. You could really again see, well, is semiclassical gravity correct, or is full quantum gravity correct? And in the light of this here, one would expect, I mean, that the semiclassical theory has problems, but no one has done this experiment. No? So versus in semiclassical theory. And so differences in potentially drastic differences. Now, another interesting topic to be discussed here, and I have no time for all the details. Again, I have to refer to literature, but I nevertheless want to mention it, that some people have used, so in the last 20 years or so, this as a motivation to discuss at the level of the Schrödinger equation, an equation with an expectation value of the Hamiltonian. Yeah. So that's not really something that has been rigorously derived from this. It's a kind of model equation that contains features of the semiclassical Einstein equations, and that has to be discussed. So this is just a remark, and this is called the Schrödinger-Newton equation. Schrödinger-Newton equation. So, I mean, the Schrödinger equation, you have I h bar d psi over dt is minus h bar squared over 2m Laplace psi, and then you have m phi psi, where this is the gravitational potential in Newtonian limit. This is what you do, and if this is just given, then you are at what we did also last time with the cow experiment and the like. But here you can make then an ansatz that Laplace phi here is okay. It's a Poisson equation, but you can write this in that form. So as if this were a mass density in three-dimensional space, but you instead write here the absolute value of the psi squared. So as if this were a mass density. Okay, actually it's a probability density, a mass density in 3 space. And of course you can then formally integrate this and write then here, I mean, you can formally integrate this for phi and put it here, and so you will have an integral over this psi squared. So we will have a complicated integral differential equation, which is different from ordinary quantum mechanics, and you can discuss it. For example, people have discussed what happens to the propagation of wave packets. Now you know we have the dispersion of the wave packet through Gaussian wave packet under the Schrödinger equation. And the point is, if you have such terms, would this be modified? And in fact, yes, it seems that there's a stronger decrease, in fact with increasing mass and so on, but seems difficult to check experimentally. Now, this is certainly interesting. So far, to my knowledge, there's no experiment that was able to distinguish between this equation and, say, standard linear quantum mechanics, but it's imaginable that such situations exist where you can test, and say people have then the opinion if maybe experiments are in favor of this equation instead of linear Schrödinger equation, it would also give arguments in favor of this. And on the other hand, if this were violated in experiments, would also be further arguments against this. Although, I mean, this is not something that follows in a derivation from that equation. So we have discussed the semiclassical Einstein equation and its limits. So to summarize, it's not crystal clear that this equation fundamentally, and if taken exactly, is wrong, but there are certainly many indications about weak points, I would say it like that, independent of the more static point discussed last time, that if you want to have a unified theory, it would perhaps seem weird to have one part, say gravity, treated differently from all the others, so having one classical and all the rest quantum, although logically this is not excluded. Let me at least have a short look at this paper of Epley and Hanna. I mentioned earlier DeWitt of 62 and also Epley and Hanna. So DeWitt, I already said that you cannot conclude that the quantum nature of one system transfers to the other system. You can have a hybrid theory. Epley and Hanna concluded that you must quantize gravity, and so is this in conflict, say, to what I just said? I don't think so. You can also find the detailed arguments in the paper by Albers et al., our paper that I mentioned earlier. But let me have a brief look. So what they concluded that gravity must be quantized. But is this really true? Now, they consider the interaction of a classical gravitational wave with a quantum system, and they conclude from these Gedanken experiments that you find contradictions, say, with energy conservation or with the uncertainty principle for the quantum system. So they consider interaction of classical gravitational waves with a quantum system. So, for example, I have here the classical gravitational waves, which by now, of course, we can measure directly by the LIGO and others interferometers. So we have here classical gravitational waves. And then you have a quantum particle, whatever you have, say, you have here that is described by a wave function, and it's in a position uncertainty. So, and this is it's assumed to be measured, this position. So we assume that lambda is much smaller than delta x. No? So there's arbitrarily small wavelengths in principle, and a negligible perturbation of the gravitational wave. So Epley and Hanna consider two alternatives. So one alternative is that a gravitational wave collapses in the sense of a quantum measurement process psi, and from this they conclude that either one has momentum non-conservation or one has a violation of the uncertainty relation. So, okay, I don't write this down here, but you have then problems when having an exact gravitational waves and here quantum system. But I would here directly reject anyway this alternative, because collapse is not part of standard linear quantum theory. Of course, we have the debate about interpretation of quantum mechanics, but definitely if you have a collapse, then you have nonlinear terms of quantum theory, and this is not the level we have. All right, so this here, but this is not part of a standard linear quantum theory. One can, of course, discuss this in so-called gravity-induced collapse models. Like with the Dieuchi-Penrose equation and so like. These are new equations where the gravitational field collapsed the wave function. But this collapse equation typically lead to momentum non-conservation, and which could be the case. In some situations, of course, but in experiment, so far this has not been seen. So that first part of the argument, I would say, at least, this is some time ago, and say from a modern point of view, now having all these collapse theories is not really the alternative. So the second option is that there's no collapse assumed, and one has standard linear quantum theory. Whether you have then the average interpretation or you have to go to the Bohr-Bohm or others does not matter. And let us assume then, following Epley and Honey, then the following, that you have, say, a particle, say a pi meson, that this decays into other particles, say 2 photons, and having, say, an EPR, Einstein-Podolsky-Rosen type of situation. Now, so we have here, this is the particle 1 and this is the particle 2, and there's also the detector here that is initially in a state, say, phi naught. And there's again, following here Epley and Hanna, then a classical gravitational wave that scatters at particle 2. So classical gravitational wave scattering at particle 2. And so they consider this EPR situation. Okay, EPR means that this is in, say, in a singlet state. I should write this perhaps down. Where you have a superposition of, say, a spin in one direction, spin in the other. So here polarization in one and the other. So this here is in a singlet state. And they claim that when we have a classical gravitational wave scattering here, and here we have a detector that measures the polarization here, that we can here, by this, instantaneously see here whether here the measurement was done. Here. Now that's not possible in standard EPR. I mean, Einstein was very much worried about this spooky action at a distance. This is why he thought about this EPR with Podolsky and Rosen in 1935. And it's clear in standard quantum mechanics you cannot really have superluminal signals. But Epley and Honey claim that you can have, if you have here a classical gravitational wave that scatters here. So instantaneous measurement, instantaneous observation of measurement that you do here, and then you would really have a violation of causality and all that. But this conclusion is not correct. Yeah. But there is no, so in this here that we have here in this version 2, so there is no superluminal propagation, even if you have a classical gravitational wave. Why? Just do standard quantum mechanics, which of course in here is assumed. So we have here, before the measurement of the polarization of particle 1, we have the following state. Okay, this is standard notation. Just let me write it down. No, okay, the detector here that measures the polarization here is switched off. So just here put here, and that's a singlet state. No? So here this is photon 1, and this here is photon 2, and of course here also. No? So you have here the I think it's clear, the standard notation of a singlet state. Okay, now you make a measurement here of particle 1 of the polarization. So this was before, after the measurement of, I should write the polarization of that it's clear what is meant of 1. Then you have the following state, and let me call it just psi. It's 1 over square root of 2, and then of course we have here 1, 2, and then we have the detector in the state where it has measured, say, spin up or polarization up, minus 1, 2, and here down. So here this means that the detector has measured the polarization down, and here the detector has measured the polarization up. Now in linear quantum gravity, this is what, according to the Schrödinger equation, this would evolve to. But you see here, photon 2 is never ever in a pure state. Yeah? It's quantum entangled with photon 1. Neither before nor after the measurement is separate in a pure state. It's always in a mixed state. Yeah? So photon 2 is always in a mixed state. No? So there's a entanglement between 1 and 2, which means that the global state only is quantum, pure state, but the subsystems, they are described by density matrices. You have to integrate out the other system. So that is both A and B lead to the same density matrix, namely the following one. Rho is 1/2 then if 2 and down, up and down. No, I understand. So you have just this mixture between the photon polarization being up and down. So whatever you do here, measure here at photon 2 in standard quantum mechanics, whether you have a classical gravitational wave or not, it's always in a mixed state, and you can never see here any direct superluminal propagation. So you see the arguments by Epley and Hanna are not really conclusive in favor of that you must quantize gravity, because otherwise you have conflicts of a fundamental nature. Now, of course, there is a difference between A and B, that's clear, but you can only see this if you bring 1 and 2 together. You have one quantum state, one entangled quantum state between 1 and 2, and only if you, for example, make an interference term, bring them together, you can see the difference between this and this, but this is not possible in a superluminal way or so. So, here, for example, you see interferences, and here you don't see interferences, you have decoherence. So you can check by making experiment with both of them whether you're on the state psi naught or on the state psi. But if you only measure one of the two, and this is far away, you have the same density matrix. Okay, so far for this discussion, and so far also for the section 1, 2. So we are basically finished with chapter 1. I have here a short conceptual outlook on what follows. So 1.3, which is approaches to quantum gravity. I think I have I hope I have convinced yourself about the need to discuss quantum gravity, even if there's no logical argument that you must, because of the unification of forces and all the limits of the semiclassical theory. So for the rest of this lecture course, actually we really do then quantum gravity and not semiclassical features or other features. The problem main is, of course, there is no direct experimental observational test. you would need, I mean, to probe the Planck scale, I mean, you would have an accelerator much bigger than the solar system, which of course will never be built. There may be a chance to have tests in astrophysics in the anisotropies of the cosmic microwave background, or with the evolution of black holes. But this must of course be checked within a certain theory and must be checked with the concrete observational equipment. But even without that, even if it takes again long for an experimental test, one should not forget what Einstein once said in a conversation to Heisenberg, and this is often quoted, that only the theory decides what can be observed. So if you have a well-defined and agreed on quantum theory of gravity, maybe then we understand in which directions we should check, in a direction that maybe now is not yet clear. Yeah, having the theory decides about potential observation, not what you have, say, what you know or think you know before having the theory. So that means we look for a mathematically and conceptually consistent and eventually empirically testable theory. But how do we do that? I mean, the problem is difficult, otherwise it would have been solved long ago, because people already in 1930 started with it. Now one can, this is what I do at the end today, distinguish between, I think, two main maybe conceptual approaches. So Chris Isham in 1987 in an article distinguished between so-called primary and so-called secondary theory of quantum gravity. Well, whether you call them primary or secondary maybe is a matter of taste, but there are two different approaches, and the primary theory of gravity is that you start with a well-defined classical theory and then you apply quantization rules, maybe in a heuristic way, maybe in a more mathematical way, and you construct a quantum theory that corresponds to that classical theory and which you have to discuss and test. And that's what we did with quantum electrodynamics or with quantum mechanics. We have the classical theory, say mechanics, and then Schrödinger devised his Schrödinger equation and so on, or the Heisenberg version of that Heisenberg picture. And then we have quantum mechanics, and we apply it, and it's extremely successful. We understand molecules, atoms, particles. So the idea would be to start with a classical theory and then to apply heuristic, more or less, quantization rules. Now you make the metric, an operator, and all that, and you arrive at a quantum theory. No, you can, well, you guess the quantum theory by this, and then you have to check here. No, so this is, for example, the case in quantum electrodynamics. And what you can do here is, of course, you can start with your classical theory that is the most accepted one, which is general relativity. No? General relativity. And then you have quantum GR. And much, not maybe even most of what comes in my lectures will be actually devoted to that. Because that's the simplest and most conservative. It may not be the correct approach at the end, but it's certainly something we would start, because general relativity is the empirically tested theory of gravity. But you can also start with others, no? You could also have, let's say, other classical theories, like the Jordan-Brandstike theory. And then you have or nowadays people discuss, for example, so-called F of R theories, where in the action you do not just have the Ricci scalar, but a function of the Ricci scalar, and so on. No? So you can start with other theories and have quantum versions. So the advantage of this is that the starting point is clear. No? So advantage of this So the starting point is clear. Well, the disadvantage is that you do not have a unification. Just by doing that. I mean, you quantize the gravitational field separately as you quantize separately the electromagnetic field. Of course, I should say here QED, that it's clear, but for example, for quantum chromodynamics, it's not as trivial, because you don't have a classical theory of chromodynamics. So one has to take this with a pinch of salt. Of course, in quantum chromodynamics, one follows a little bit the structure of this, but it's not just quantizing a classical theory. So in principle, there is also a subset of this A1 where you have a classical theory that you have tested, and A2, where the classical theory is maybe not really existing, like chromodynamics. But the difference is here, I mean, between A and B, and so here B means you start, or you construct a fundamental quantum theory of all interactions. By whatever means. I mean, that's maybe you guess it, or you have some principle and so on, like Einstein had the equivalence principle. So you construct, and then you derive quantum gravity in some limit. In this fundamental theory of all interactions, there's not yet maybe a separation between gravity and Young-Mills fields and others. There's something totally different, but of course in some limit then it should contain quantum gravity. Or this is why we also call this emergent gravity. And of course the main example is string theory, but maybe even the only one. So example, string, or nowadays called M theory. I mean, also string theory is constructed by quantizing something classical. I mean, as a one-dimensional string in an external background, but it's not classical relativity that you quantize. I mean, it's something else, and once you have that, I mean, you want to derive, I mean, quantum general relativity, then at the end even classical relativity in some limit. You must not think that A and B is totally different, because here use also many tools that you use here, like quantization of constraint systems and the like, perturbation theory, and so it's not that here, I mean, this is totally disconnected, but you really don't start from a quantum version of a classical gravitational theory. And so it's clear, so here the advantage of this is that you really have a unification, right? But the disadvantage is that the starting point is not clear. So I mean, you may spend some decades to work on, say, a theory like string theory, and at the end it turns out to be not the correct one. Whereas here, at least you are with a starting point very close to what you know, and you might expect that at least some part of the truth is preserved by this. Of course, here in A, it's not just one formalism. So we will here see there are different formalisms. So the so-called covariant approach that we do next, and the so-called canonical approach that we do later. And also there, depending on which variables you use, they are different. And it's maybe expected but not clear that these different formalisms are equivalent. Of course, you don't have to necessarily have string theory. You can have with say, other theories, typically maybe discrete theories of gravity. um, where you impose some discrete structure. I will occasionally spend some word on them, but we will not have the time to systematically discuss it. Okay, that's more or less chapter 1. So I'd like to end with a historic remark. So the very first person who already remarked towards the need of quantum gravity, who was that? Yeah, if you don't know, you may be surprised. It was Albert Einstein already in 1916 when he had his paper on the gravitational waves. Because, yeah, one knows that, or knew at that time, that classical electrodynamics leads to inconsistencies. I mean, the atoms would collapse because, I mean, the electrons would spiral into the nuclei and so on. And so after, at least, I mean, it was 1916 was before the advent of quantum mechanics, but you had Bohr model and so on. So you have these stationary levels. And after gravitational waves, at least theoretically, were encountered by Einstein, he thought, okay, then you must apply the same also to gravity, because otherwise also you have this instability. And let me quote him first in the original German. He wrote, gleichwohl müssen die Atome zufolge der inneratomischen Elektronenbewegung nicht nur elektromagnetische, sondern auch Gravitationsenergie ausstrahlen, wenn auch in winzigem Betrage. Da dies in Wahrheit in der Natur nicht zutreffen dürfte, so scheint es, dass die Quantentheorie nicht nur die Maxwell'sche Elektrodynamik, sondern auch die neue Gravitationstheorie wird modifizieren müssen. So, in the same way, the atoms would have to emit because of the inner atomic electronic motion, not only electromagnetic, but also gravitational energy, although in tiny amounts. Since this hardly holds true in nature, it seems that quantum theory will have to modify not only Maxwell's electrodynamics, but also the new theory of gravitation, which is his own theory. So you see, even immediately after having constructed general relativity, he already pointed to the limits. Of course, this was in the context of what we now call the old quantum theory, Bohr's model and all that. And you know that Einstein later was very skeptical about quantum theory. I mean, in the context with this Einstein-Podolsky-Rosen discussion and so on. But still, this old argument holds. No, if you have gravitational waves, and at least that gives you a hint also about the quantum nature of the gravitational field. And now we have to enter the detailed work, I mean, of constructing such theory. And next time, and also in 2 weeks, we discuss the so-called covariant quantum theory of gravity. See you then. Bye-bye.